All right, math addicts, here we are again with another installment of mathematics with Mr. Stephen Haas, and today we're going to talk about the logarithmic function, which is pretty amazing. The logarithmic function is the inverse of the exponential function. So we know how inverse functions will go from one function back again. So it's very important to remember they're inverses of each other. And here's the definition. The log base b of x equals y if and only if b to the y equals x. Now, b is the base, and this has to be larger than 0. Might be small, like a fraction or something, but larger than 0. And we're not interested in b equals 1 because that's just trivial. 1 to any power is just 1, so it doesn't matter. And x inside here will always be positive. All right, so this you really need to tattoo somewhere on the cortex of your brain without interfering with language or music, but somewhere you need to tattoo this inside your brain. This is not something you want on a card or something you refer back to. You want to have this so you can immediately pull it up. It's not hard. And the way to remember it is the log. What we have down here is the base. So this is the base. This is our b. What's inside the log is called the argument. That's inside the log, and this equals y. Look at y here. What is that? What's y? That's an exponent, and y is equal to the log of x. So this is the exponent. So now it's the base, and this is if and only if the base of the exponent with raised to the exponent power equals the argument. So the main thing to remember is here's the base and here's the exponent. The exponent is equal to the log. So a log is an exponent. This is very important. Always remember, when you're talking about logs, you're talking about exponents. All right, let's do some problems. What we're going to do is we're going to convert logarithms into exponentials. So here's what we do. We take the base. This is true if and only if the base is 10. This is the exponent. So this is the base. This is the exponent. And it equals the argument. So that's the way you always want to write it. That's the base, that's the exponent. That's the way I kind of remember it. That's the base, that's the exponent. The argument is kind of left over. It goes in the place that's left over. So let's take this one. Log base 3 of 81 is 4. If and only if the base is 3 to the 4th power equals 81. Log base 3 of 81 equals 4. So 3 to the 4th equals 81. You want to be able to do this in your sleep. You want to have this down pat. All right, so let's see. Let's take a look at this one. This is true if and only if 3 to the negative 3rd power, the negative 3 power equals 1/27th. Okay, is that true? Well, let's see. 3 to the negative 3rd is 1 over 3 cubed. So, and that's equal 1 over 27. So everything looks okay there. Okay, so let's go the other way. Let's turn this into a logarithm. This is true if and only if the log And here's our base, 5. This is the argument on the inside, 125 equals the exponent. So actually the reason for this is we can work with problems like 7 to the x power where we want to solve for x. We can solve functions where x is the exponent. And the only way we do that is we make it a log function. So we take it out of being an exponent. That's why the log function is so nice. So now let's take 1/4. So we have the log base 1/4. And this is okay because it's larger than 0 of 16 equals -2. All right. Now, it's very important. This number is smaller than this number. This isn't a power of this one. I see people write log base 2 of 8 equals 3, which is true because 2 cubed is 8. 2 to the 3rd power is 8. I see people write this log base 2 of 8, and this is wrong. We're used to making the number up here smaller because it's a power. This is not a power. The argument is bigger than the base, so that's real important to remember. All right, let's get a few properties of logarithms. Now we're going to have a number of properties, and these are the first couple of properties. We'll get more laws as we go on, how you work with the product of logs, the division of logs. But first of all, let's look at this one. The log base b of b to the x equals x. Now this makes sense because here's an exponent. Here's an exponential function, b to the x. If we take the inverse of that, we should get x back, because that's what the inverse does. And so here's why. This is true if and only if the base b to the exponent equals the argument. So there's a proof. That's obviously true. Let's take, under these we have some corollaries. Like this one here, log base b of itself is just 1. So let's rewrite this, an exponential. The base to the exponent equals the argument. So that's true. Let's take this one. We've got b, the exponent is 0, and that is certainly 1. And these are just part of this one. This one, the x is 1. This one is b to the 0. That's what 1 is. So these are just corollaries of this rule right here. Now this is the inverse function, right? If you take the log of an exponential, you just get the x back. In the same way, if you take an exponential of the logarithm, you'll get the x back. So we take the log base b of the argument equals the exponent, and here's the exponent. So that's obviously true. See, we've taken the log base b of the argument has to equal the exponent. So this is true. All right, we have special logs. One of them we call the common log, and the other one we call the natural log. The common log is the log base 10 of x equals y. And the reason this is common is that we use a base 10 for our number system. So we remove the 10. If we see the log of x equals y, we know that that's a 10 here. And on your calculator, you have a log button. This is always just base 10. All right, this is the common log. The natural log is the log base e of x equals y. Now, we've already talked a lot about e and how important it is, and that's why we use it so much, we might as well use a shorter notation. We go the ln. ln means the log base e. ln of x equals y. So we have an ln button on the calculator, and that's just log base e. Let's talk about the graph to kind of get a feeling for this. Actually, let's do the graph of the natural log. So first of all, if we take, and this will just be a rough graph to give you an idea. If this is y, I said y and it went x, it's supposed to be x, and this is y. If we take the exponential function, you remember this looks kind of like this. This is f of x equals e to the x. And this point here is where x is 0 and y is 1. It's the y-intercept. So put it in there. E to the 0 is just 1. All right, now the log function is the inverse. And now we're going to call it the ln of x. We want to move away from this and start calling it the ln of x. Now, what do we know about the graphs of an inverse compared to a regular function? Remember? We've changed the x and y, so it's a mirror image about the xy axis. So if this is our, that's not quite 45 degrees. Let's see if I can do that a little better. So this should be the mirror image. That means over here, we're going to have the point 1, 0. When x is 1, y is 0. We're on the x-intercept. And this will look something like this. So this is f minus 1 of x equals the ln of x. So it's the mirror image of this one, of course, because they're inverse functions. All right, here's some problems. Let's start with this one. We have solve for x, the ln of 3x minus 1 equals negative 2. So first of all, remember, the ln is the log base e. So now this x is inside an ln. We can't solve it our normal way, but if we can pull it out by doing the inverse function and make it an exponential. So we go e, all right, to the exponent equals the argument. See how nice that is? Now we've got the x on the outside and we can solve for it. So this is e to the negative 2 plus 1 equals 3x. If we divide both sides by 3, we've got e to the negative 2 plus 1 over 3 equals x. So now we solve for x. Okay, here's another one. The log base 9 of x equals 0.5. So again, the x is inside the logarithm. We can't work with it. We just change it to an exponential. The base is 9. The exponent is 0.5, and that's x. So we actually solve for x, but we can simplify this. This is 9 to the 1/2 power equals x. And what is 1/2 power? Do you remember what 1/2 power is? It's the square root. So the square root of 9 equals x. So x equals 3. And if we put this in here, 9 to the 1/2 power equals 3. Okay, so now let's solve this. Here's one where we have it as an exponent. We can't solve it as an exponent. We can turn this into a logarithm. So this one, we say the log, the base is 7. The x, this is our argument, and that's our exponent. So there's our answer right there. Now, we're going to this is the exact answer for what x is. I know it's not a number, and we'll show you how we can find out what this actually is in terms of a number, and we can approximate it with a calculator. A calculator can't tell you exactly what that is. All I can do is approximate it to 10 decimal places. All right. And so for the last one, again, the x is in the exponent, so we have to use a logarithm. So the log, our base is 6. This is the argument, and equals x minus 4. Again, make sure your base is smaller than your argument. So all we have to do is add 4. This is the log base 6 of 2 plus 4 equals x. Now we have to be careful here. We don't want to add the 2 and the 4, so you might want to write this x equals 4 plus the log base 6 of 2. All right, we'll see you in the next video.